let's begin. So there is a difference between ordinal numbers and cardinal numbers. Cardinality means size and ordinal number denotes position in a list. Okay, so first, second, third, these English letter words are different than 1, 2, 3, correct? Then zeroth is also added for formality. I mean, zero is nothing, so nothing exists and therefore everything exists, old joke now. So ordinal numbers denote the position. So whenever we are listing, so suppose you list all integers, how did we do that? You remember? 0, 1, minus 1, 2, minus 2 and dot dot dot. So in this particular list, minus 1 is the 0, 1, minus 1, 2, minus 2 dot dot dot, minus 1 is the third. So you know that in this list the position matters, correct? The position of that particular number matters, and those are denoted by ordinal numbers. Whereas if I just say 0, 1, minus 1, 2, minus 2 and then I ask the question how many are there, then the answer is 5. So how many and which position, these are two different questions, so the same numbers have different purposes. However, when we go to infinities, then the answer won't be the same. So the position in an infinite situation is different from the size, and that is the difference between ordinal and cardinal numbers, which is what our next topics are going to be. So in order to understand that, let's look at this first definition. What is a linear order? A strict linear order, it is an irreflexive transitive binary relation. Yeah, we have seen that. So real numbers with respect to strictly less than, that is a strict linear order. Natural numbers with respect to less than or with respect to belonging, if you remember. Yes, less than is same as belonging. Then rational numbers, any finite number, finite natural number, yeah, that's also a strict linear order with respect to belonging relationship. Okay, and just to remind you what are for natural numbers, I mean I'm calling them ordinals because we'll enlarge this list today. So 0, which is the empty set, is a natural number, and if n is a natural number, then so is n plus. N plus, all of you remember? N plus is n union singleton n, and because of axiom of foundation, n doesn't belong to n, and therefore this is a strictly bigger set. So it is the so-called successor of n. Okay, very good. So now another definition that we'll need, a strict linear order isomorphism between L1 less than and L2 less than is a function f from L1 to L2 satisfying x less than y in L1 if and only if fx is less than fy in L2. Is it hard to understand? It's a function which preserves, yeah, so if x is less than y, then fx is less than fy. This is like a homomorphism property. It's a monotone map. It's a strict monotone map. It preserves, but it also reflects. It not only preserves, but it also reflects. As in, whenever x and y are two elements in L1 and fx is less than fy, then x has to be less than y. Okay, so preserves and reflects or strict order relation. By the way, I forgot something. the first two properties here, they only define a strict partial order and not a linear order. I missed the third property, and that third property is trichotomy. Very good. So for all x, y, z in L, yeah, if x is not equal to y, then either x is less than y or y is less than x. Yes, okay. Sorry about that. So this is a strict linear order isomorphism here.
Sir, why are we using the word strict here?
Because normally what do we do? L less equal. We also include equality in that. So in that case, irreflexivity is replaced by reflexivity, then we have transitivity, we also have trichotomy, and we have one more condition, antisymmetry. Yeah, if x is less equal y and y is less equal x, then actually x is equal to y. So in that case it will be a weak linear order or just a linear order. Yeah, but here I am purposely writing strict linear order.
So here f should be a bijection.
Yes and no. F doesn't need to be a bijection because of this condition. X, any two elements are related. So if x is less than y, then automatically fx less than fy implies that because of irreflexivity of L2, that fx and fy cannot be the same. Oh, maybe I should say that. It's not necessarily guaranteed to be surjective. It is a bijective function. Okay, it is a bijective function which satisfies this. I should have said it is a surjective function, it is sufficient, but let's keep it a bijective function. Any other questions? Okay, good. So now that we know these things, we want to look at one particular type of strict linear orders. A well-ordered set which we will abbreviate as VOSET. Okay, well-ordered set, VOSET. Partially ordered set is called a POSET. Yeah, so well-ordered set is a VOSET. Is a linear order, is a strict linear order, W less than, such that every non-empty subset of W has a least element. Okay, least element means it is smaller than any other element in that subset. Right? So, for example, let me take 2. What is 2? 0 and 1. This is a VOSET. With respect to belonging relationship. Because what are non-empty subsets of 2? Singleton 0, singleton 1, or 2 itself. Singleton 0 has 0 as the least element, singleton 1 has 1 as the least element, and 0, 1 has 0 as the least element because 0 belongs to 1. Okay, similarly, n comma belongs to is a VOSET for each n in omega. Every natural number is a well-ordered set. Yeah, if I give you 0 up to 100 and then I give you a non-empty subset, can you choose the least one? Yes? Yeah, so that therefore this is true. However, 0 comma 1 subset of R is not a well-ordered set? Can you tell me which subset doesn't have a least element in 0, 1? The set itself, right? Because if the minimum has to exist, then it should be 0, but 0 doesn't belong, right? So therefore it is not a well-ordered set. Is the set of real numbers well-ordered? Rational numbers? Integers? Yes and no. Yeah? No, integers is not, because the whole integers do not have a least element. Okay, so well-ordered sets are scarce. Yeah, one more thing. Note that omega less equal or omega strictly belongs is also a VO set. If I give you any non-empty set of natural numbers, then it contains a least element. Yeah, you can prove that. It's a bit tricky, but you should try that. Yeah, that it follows from axiom of foundation, or the way we have designed these things. Okay, so this is also a well-ordered set. So omega is a well-ordered set. So far what do we know? 0 is well-ordered, 1 is well-ordered, 2 is well-ordered, ... Omega is well-ordered. Okay, I am also going to give you that suppose x is equal to 1, 2 with 1 less than 2 as the relation. So this is our less than relationship. Then is x well ordered? Then x comma less than is a VO set. Okay, but now comes the interesting thing. Please look at what we wrote here. A strict linear order isomorphism is a bijective map which preserves and reflects orders. So can you tell me if X is isomorphic to any other well-known linear order? Something from our list? 1 and 2 is isomorphic to, X is isomorphic to 0, 1, right? 0 maps to, like from 0, 1. So so define f from 2 to x, which sends 0 to 1 and 1 to 2, so that f is a strict linear order isomorphism. Right? So in fact every finite well order is isomorphic to the unique natural number, which is its size. Right? So every finite well ordered set W less than with size n is isomorphic to n comma belongs. Do you agree with this? You understand how to do it? If I am given a well-ordered set, then I will choose the least element. Yeah, by property of a well-ordered set, the least element exists. I will send that least element to 0. Then I will remove that, and accordingly I will also remove 0 from the other side. And then I will again ask, what is the least element? I will send that to 1, and then again remove that. What is the least element? And I continue this procedure. I will get an isomorphism. Isomorphism is simply renaming. Correct? So every finite well-ordered set is isomorphic to n comma belongs to. Yeah, belongs to is the order relation there. Any questions so far? Size n, yes, yes. I mean, we know that what is the meaning of finite set? That it is in bijection with some n. But here I am not choosing an arbitrary bijection. I want that bijection to preserve and reflect the order relation also. Yeah, so we want that bijection to do something more. Understood this?
Sir,
Yes.
can you explain why real number is not a whole set?
Why real numbers are not a well-ordered set. Okay, if real numbers are a well-ordered set, then there should exist a minimum element in real numbers. Does there exist a minimum, like smallest element? No. Integers also don't have it. Yeah. Closed interval 0, 1, does there exist, like is it a well-ordered set?
Yes.
No. See, closed interval 0, 1 contains open 0, 1. And open 0, 1 doesn't have a least element. Understood? No continuous, yes, no non-empty interval can be well ordered.
So in a continuous set,
What is the meaning of continuous set? I did not want to say that. That's why I said non-empty interval, which contains at least two elements. Yeah, that cannot be a well ordered set. Any other questions? So now loosely speaking, yeah, very loosely speaking, the isomorphism classes of well-ordered sets are called ordinals. Okay, let me repeat. The isomorphism classes of well-ordered sets are called ordinals. Now recall, what is cardinality? Equinumerosity classes of sets, they are called cardinal numbers. However, there is a problem, yeah? Equinumerosity class. So it's a proper class. We don't want to deal with that. And similarly, the isomorphism classes of well-ordered sets, they will form a proper class, and therefore we don't want to deal with them either. So whenever we have a problem with classes, then we simply choose a representative. Understood? We have a partition of the entire thing. So I mean, I'm just going to write an ordinal, and this is an informal definition. I will make it more precise. An ordinal is an isomorphism class of well-ordered sets. Yeah, this is not a definition. So maybe, yeah, this is the collection of all well-ordered sets, and then up to isomorphism I partition them like this. Our job is now to find one particular well-order from each class, and we'll call that an ordinal instead. Okay, similar to bijection. So bijection equivalence classes of finite sets, what do they contain specifically? Finite sets? One natural number, a unique natural number, and then we say that that unique natural number is the cardinality of our set. Similarly, every isomorphism class of well-ordered sets will contain a unique nice set, nice well-ordered set. So so what can we say? Yeah, if W less than is a finite Vo set, then the ordinal isomorphic to it is n comma belongs to for some n. Yeah, we just saw that. Every finite well-ordered set is isomorphic to n comma belongs to for some natural number. I mean, which natural number? It is precisely the size. How many elements are there in it? So similarly, now we want to do this for infinite linear orders as well. Infinite well orders. And then we will define our set to be something. Okay, so now I am going to define a new concept, and that's called a transitive set. So a set X is said to be transitive if for all y in X, y is also a subset of X. Very confusing, right? Belongs to subset. I will rewrite it equivalently, and I will give you a motivation why it is called transitive. So for all y in X and for all z in Y, Z also belongs to X. Now, does that give you a feel of transitivity? Z belongs to Y, Y belongs to X, therefore Z belongs to X. Yeah, that is precisely this statement. If Y is an element of X, then Y is also a subset of X. Yeah, what is the meaning of subset? That every element of Y is also an element of X. So therefore these two are same. So some examples. Empty set, obviously. All the nice properties are true of empty sets. Then 1 is transitive, correct? 2 is transitive, it contains 0 and 1, but it also contains the element of, no, 0 doesn't have any element, but 1 has an element, so it contains element of 1 as well. In general, n is transitive as well. Yeah, because something belongs to n means it is less than. Then if some, so let's say m belongs to n. Then if k belongs to m, then k is less than m, then by transitivity k is less than m, m is less than n, so k is less than n. So therefore every n is also a transitive set. Okay, good. So what about omega? Omega is transitive or not? It is. Yeah, you choose any element of omega. What is it? It is a natural number. And what is an element of natural numbers? Another natural number, so that's also there. So it is also a transitive set. But this is not all. Yeah, we can add a few more. Yeah, so for example, consider this. Something which contains 0, something and singleton 0, which is 1, and singleton 0. Now observe this. Yeah, this is transitive because it contains all elements of this, which is namely this. It contains all elements of this also, because one element is here and then its element is this. So this is also transitive. So all of them are transitive sets. Now, not all of transitive sets are well orders with respect to belonging relationship, membership relation. Yeah. So note not all transitive sets are वो sets with respect to membership relation. I mean, what is a contradiction? What is a counterexample to this?
The first and the third one.
First and the third one. Yes. In this particular set, if I choose 0 and singleton 0, then it is a non-empty subset. But does it have a least element? Yeah, I mean, let me call this W, okay? So 0 comma singleton 0 subset of W, and this is a non-empty subset, doesn't have a least element. Because what is the problem? If it is supposed to have a least element, then because 0 is not an element of singleton 0. Understood? So therefore, transitivity is an independent property. Being well ordered with respect to membership relation is an independent property, right? Because we found an example. Okay, so, and there are many more well ordered sets. So for example, consider this, this x is equal to 1 comma 2. This is a well ordered set, but it is not transitive. Is it transitive? What is the meaning of being transitive? That if you choose any element, then its element should also be there. So I chose 1, but the element of 1 is 0, and 0 is not present in this set. So this x is not transitive. It is a well ordered set, but it is not transitive. So there are some well ordered sets which are not transitive. There are some transitive sets which are not well ordered with respect to membership relation. But what we are interested in is an ordinal is a well ordered set W comma belongs to that is also transitive. Now this is the real definition of an ordinal. It is a well ordered set that is also transitive. So do you know any ordinal numbers? 0, 1, 2, 3, omega, omega is also transitive, it is also well ordered set. So you know many examples. These are called von Neumann. See, f, not v, von Neumann ordinals. Okay, so I am just going to write down a few von Neumann ordinals. Zero, 1, 2. All of you are okay with this, right? Then omega. Omega is also transitive and well ordered set. What about omega plus 1, which is defined to be omega plus? It takes some time to prove this. We'll do that in a moment. But yes, omega plus 1 is also an ordinal. Omega plus 2, which is omega plus plus, is also an ordinal, and whenever you say dot dot dot, then ultimately omega plus omega, which is also which is defined to be omega dot 2, is also an ordinal. Then, well, I shouldn't stop at omega dot 2. Its plus is also an ordinal, so means I can add 1, I can add 2, then I can go up to omega dot 3, which is omega plus omega plus omega, and don't stop there. Omega dot 4, omega dot 5, and dot dot dot. Omega dot omega, which we write as omega square, then omega square plus 1. Yeah, again add 1, add omega, continue. So ultimately you will have omega square plus omega, then omega square dot 2, and omega cube, and you continue like that, then you will have omega to the power n for any n, then you will have omega to the power omega, right? Then eventually you will also have omega to the power omega to the power omega, and if I continue like that, then I will have epsilon naught, which is defined to be omega to the power omega to the power omega to the power omega, and dot dot dot. It never ends. Yeah, so it is the smallest solution of epsilon naught is the smallest solution of the equation omega to the x is equal to x. Right? This is an infinite tower. So that infinite tower is solution its own omegath power also. Then again I can do epsilon naught plus 1 and continue. I will have epsilon 1 at some point. I am not going to define what that is. And eventually, yeah, okay, one more thing, these are all sets. Yeah, these are all sets. And not only that, these are all countably infinite sets. After, yeah, I mean after finishing finite linear orders, these are all countably infinite sets. Omega is countably infinite, omega plus 1 is countably infinite, you are adding just one more element, right? All of them are countably infinite, even epsilon naught is countably infinite, so it's a small ordinal. It looks really big, but it's a small ordinal. But ultimately you will run out of countably infinite ordinals. Can you give me a reason why? That will run out of countably infinite ordinals, and if we want to continue with the process, then we have to hit something uncountable.
Same reason that we run out of finite ordinals at some point.
Okay, what is that reason? Why do we run out of finite ordinals at some point?
You can't have a set that contains all.
No, I want more formal reason. So we are talking about all of them being well-ordered sets which are countably infinite. So up to isomorphism, I am defining different well orders on natural numbers itself. If all of them are countable, then I am defining well orders on natural numbers. It's a different ordering. Yeah, for example, this omega plus 1, what is that ordering? Well, this ordering is 1 less than 2 less than 3 less than dot dot dot, and 0 sits at the top. That is the ordering on natural numbers, which gives me omega plus 1. If I want to talk about omega plus omega, then actually I am talking about 1 less than 3 less than 5 less than dot dot dot, and all even numbers are sitting at top of them. So I am just making different arrangements of natural numbers. You understand that? That's a copy of omega 135. That's a countably infinite set. It's a copy of omega followed by another copy of omega. 2, 4, 6, I mean sorry, 0. I should write 0 somewhere, and yeah, 0, 2, 4, 6 and dot dot dot. So it's a copy of omega followed by a copy of omega. That's why omega plus omega. So these are all well orders on the set of natural numbers. And how many well orders on the set of natural numbers can there be?
Strictly less than fun and the size of fun.
The size of?
Strictly less than the size of set of functions from n to n.
Yes, strictly less than the size of, not set of functions from n to n, but the binary relations, however many binary relations I can define on natural numbers, which is power set of n cross n. Power set of n cross n is my boundary. I cannot go beyond that. Understood? Okay, so that's the reason that eventually we will run out of countably infinite ordinals. And then finally we will hit omega 1. This is the first uncountable ordinal. Then again I can do omega 1 plus 1 and omega 1 plus omega and dot 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 and omega 1 dot 2, and everything will continue. Then eventually we will have omega 2. Omega 2 is the ordinal. It is the first ordinal which is not in bijection with omega 1. Right? So we started with omega. That was our first countably infinite ordinal, but eventually we ran out of all such things, so therefore we hit omega 1, which was not in bijection. So everything in between, I am going to use a green color, everything here in this green bracket is countably infinite, which means it is in bijection with omega. Then everything in this interval is in bijection with
Power set of n.
Oh, no, not power set of n, just omega 1. It is in bijection with omega 1. Then we will have omega 2, and well, after omega 2 you can guess what it will be. Omega 3. Then we will have omega sub omega eventually. Then we will have omega sub omega plus 1. Then we will have omega sub omega dot omega epsilon naught. Then eventually we will also have omega sub omega 1, and you can make a joke out of it. It never ends. Okay, so this is the beauty. These are all different infinities. Okay, I promise to you that there will be a gradation of infinities. Omega represents an infinity which is smaller than omega 1. Omega 1 is smaller than omega 2. So omega sub alpha is less than omega sub beta if alpha is less than beta. And you can imagine this is a hard thing to understand. We have already studied the sizes. For example, natural numbers and real numbers. Natural numbers can be embedded inside real numbers, but real numbers are far more than natural numbers. So even for size comparisons, these are different. You understand? So every set is strictly smaller in size compared to its power set. Cantor's theorem, the first theorem that we saw in this course. So this process actually never ends. And what I have given you are only a few von Neumann ordinals. I haven't listed them all. They all can be studied properly. They have some nice properties. We will see how to add, how to multiply, and how to exponentiate these ordinals. But you understand the procedure here, what is happening? Now, even if you say you do, you don't really do right now. Yeah, because I haven't told you how to obtain the next one. So for example, if I am given 0, how do I obtain the next ordinal? 0 plus, very good. So that's a successor ordinal. So every ordinal is of one of the 3 types. Okay, so ordinals are of one of the 3 types. Okay, the first one is something, I am going to leave it. Second one is successor ordinals. So they look like alpha plus for some alpha. Then there are some ordinals which are like omega. Omega is not a successor of anything. Omega doesn't have an immediate predecessor. So those such ordinals are called as limit ordinals. So these are not successors. And what is number 1?
0.
Yeah, 0 is not termed as limit or successor. Some people will say that it is a limit ordinal, yeah, because it does satisfy. It's not a successor of anything. Yeah, but I would like to distinguish between these 3 things. So what's our job? Yeah, we still have some time. So let us prove our first result about ordinals. If alpha is an ordinal, then also we'll always use Greek letters alpha, beta, delta, gamma for denoting ordinal numbers. If alpha is an ordinal, then so is alpha plus. This is our first result about ordinals. So what do we need to prove to show that alpha plus is an ordinal? Alpha plus is a voset with respect to, yeah. And second thing, so alpha plus belongs to is a voset. This is the first thing we'll say. And the second part is that it is transitive. Okay, good. So alpha plus belongs to is a voset. I'm sure you can tell me the proof. So let S be a non-empty subset of alpha plus, which is what? Alpha union singleton alpha. Okay, so if alpha intersection S is empty, okay, so S can intersect alpha or not. If alpha intersection S is empty, then what will happen? Then what is S? No. Then it has to be the only element possible. It is singleton alpha. And alpha is the least element in S. Yeah, because there is only one. So there is nothing to prove here. On the other hand, otherwise alpha intersection S is non-empty. In that case, what will happen? It is a subset of alpha. Yeah, then alpha intersection S is a subset of alpha, and alpha is well ordered. So therefore minimum of alpha intersection S, yeah, the least element, will exist for alpha, and yeah, I mean as a subset of alpha, this has a least element. Now even if S contains alpha as an element, yeah, because we are just talking about alpha intersection S, but the only other element is alpha itself in alpha plus. Even if S contains alpha, this minimum is also going to be smaller than that. Correct? So therefore, minimum of alpha intersection S is also equal to minimum of S. Yeah, I mean, I'm just saying argue that. So therefore, we are done proving that alpha plus with respect to membership relation is a well-ordered set. It was easy. Yeah. Second property that we need to prove, that alpha plus is a transitive set. So suppose beta is an element of alpha plus. Suppose beta is an element of alpha plus, then what can be the options for beta? Either beta is, if either beta is an element of alpha or beta itself is equal to alpha. Those are the only possibilities. Yeah. So either beta belongs to alpha or beta belongs to singleton alpha, which means i.e. beta is equal to alpha. So these are the only two possibilities. Now what happens if beta belongs to alpha? If beta belongs to alpha, then beta is a subset of alpha. Since alpha is transitive, moreover, alpha is itself a subset of alpha plus. So therefore, beta is a subset of alpha plus. That's what we needed. Right? Okay. Now if beta is equal to alpha, then beta is automatically a subset of alpha plus. So we are done. The proof is complete. So what did we show so far? That successors of ordinals are again ordinals. Next time, yeah, which will be in next Wednesday, we will start with this proof. Yeah, so if S is a non-empty subset, oh, maybe I should use this time to prove define something else. Denote by ON, capital ON, ordinal numbers, the class of all ordinals. Now ON is the notation. In next lecture we will prove that ON is in fact a proper class. Yeah, it's not a set. And another theorem that we will prove, if S is a subset of ON, what is the meaning of subset of a class? It is a set and it is contained, right? If S is a subset of ON, then union of S is also an ordinal. Okay, why this is important? Because see, what is omega? Omega is the union of everything that we took so far. 0, 1, 2, 3, dot, dot, dot. What is omega plus omega? It is union of 0, 1, 2, 3, then omega, omega plus 1 and dot, dot, dot. So that's the other way of generating ordinals. We start with 0, then we can do successors and we can do unions of sets of ordinals. Okay, let's end it here.